Hey guys, it's Mr. Mannix again, and welcome to our second lecture video. This video is going to focus on potential energy and how we do some potential energy calculations, namely gravitational potential energy calculations. So, what is potential energy? As we talked about in class, lots of things have energy that aren't moving. In other words, lots of things have the ability to cause change that aren't moving. Take this catapult, for instance. If this rope were cut, this would definitely cause some change. It would definitely shoot this person into the air. There's definitely some stored energy there. So potential energy is a type of stored energy, and there are many different types, such as elastic potential energy. This human slingshot is an example of elastic potential energy. So these elastic bands here are tied to a cage down here, and this cage is absolutely rocketed into the air when this cage is released, carrying its passengers with it, and hence the exciting fair ride. So there's a lot of stored energy in these stretched bands, and that's a type of elastic potential energy. It's the same type of energy that is stored in a stretched rubber band, or that is stored in a bent ruler or a bent board. Anything that is deformed and tries to spring back to its natural shape or condition has elastic potential energy. There's also chemical potential energy, energy stored because of the arrangement of atoms in something's bonds. So dynamite has a lot of chemical potential energy stored in it. If you light dynamite, it explodes, has the ability to cause a lot of change. Food has the same type of chemical potential energy. When you digest food, you are releasing the energy stored in the bonds in that food's molecules. This is also energy that's stored in wood when wood is burned. Gasoline has chemical stored energy in it. That's why it can power our cars and cause our cars to move down the side of the road. There's gravitational potential energy. Anything that is found in a gravitational field and is above a surface, it has room to fall, has gravitational potential energy. So this rock up here certainly has some gravitational potential energy. And this skydiver, while he definitely has kinetic energy, also has some stored gravitational potential energy. There's stored energy there that has the ability to cause change. There's nuclear energy. Nuclear energy is the kind of energy that powers our sun. This is where all the light and heat in the sun is generated in what's called a fusion reaction. So again, the sun uses a nuclear reaction called a fusion reaction, where two atoms are slammed together and form a bigger atom. So a hydrogen and atoms are slammed together to form helium atoms. And this releases a lot of energy. Again, that's what powers our sun. Another type of nuclear energy is a fission reaction. So the reactions in atomic bombs and the reactions in nuclear reactors today are fission reactions, where atoms are actually split up into smaller atoms. So this is a larger atom here that's split into two smaller pieces of that atom. This is a fission reaction, and it also releases a lot of energy. And again, it's where nuclear power comes from. So there's energy stored in the nucleus of atoms, and it's released whenever atoms are joined or split. All right, there's electrical potential energy. Obviously, batteries have the ability to cause change. When we hook a light bulb up to a circuit, this light can turn on. When we put batteries in a toy car, it can drive across the floor. Batteries have the ability to cause change and store electrical potential energy. Closely related to electrical potential energy is magnetic potential energy. So just like there is energy in a gravitational field, there is energy in a magnetic field. So you can imagine two magnets that are separated by a small distance, if let go, might snap together. That's definitely a change. So there's energy in magnetic fields as well. All right, back to gravitational potential energy, or for short, we can call it GPE. Okay, let's look at how we can calculate how much gravitational potential energy an object has. To start with that, let's look at a graph. In this graph, we have energy in joules on the y-axis, and height in meters on the x-axis, and this is for a 1 kilogram object. So as this object goes up in height, his kinetic energy goes up. Let's see how much. So if we go from a height of 5 meters to a height of 10 meters, at 5 meters we have a kinetic energy of 50 joules. And at 10 meters above the ground, we have a kinetic energy of 100 joules. So if our height doubles, then our kinetic energy doubles. 5 times 2 is 10, 50 times 2 is 100. If our height triples, 5 times 3 is 15, then our kinetic energy triples. 50 times 3 is 150. Potential energy can actually be calculated with this equation. Gravitational potential energy equals mass times gravity times height. This gravity is the acceleration due to gravity, which on Earth happens to be 9.8 meters per second squared. So, let's apply this to some calculations. First of all, let's look at this equation really quickly. What things affect something's gravitational potential energy? There are 3 of them. One is the object's mass. Okay, the larger the mass, the more gravitational potential energy it has. So a very large boulder would have more, that was at the same height, would have more potential energy than a small pebble. Gravity also affects it. So the stronger the gravitational field, the more gravitational potential energy is stored. And the height in that gravitational field something's located at affects its energy. So something that's 10 meters above the ground has more energy than something that's 1 meter off the ground. All right, on to the calculations. What is the gravitational potential energy of a 60 kilogram skydiver when she is 2,000 meters from the ground? So, we know our equation is that GPE is equal to mass times gravity times height. What's given to us in this equation? They gave us the skydiver's mass. They gave us the skydiver's height. Okay, they're asking us for the gravitational potential energy. So we know that mass equals 60 kilograms. Height equals 2,000 meters. And they want to know the gravitational potential energy. So it might appear that we don't quite have enough information to solve this problem, but we actually know one more thing. We know that if we're on Earth, that g, the acceleration due to gravity, is always equal to 9.8 meters per second squared. So let's plug these in and solve. GPE is equal to mass times gravity times height, so it equals 60 kilograms times 9.8 meters per second squared times 2,000 meters. Therefore, gravitational potential energy is equal to 60, type it in my calculator here, times 9.8 times 2,000 equals 176 joules. 1,176,000 joules, which, remember, a joule is a kilogram meter per second squared. By the way, one misconception that a lot of students have is that because the units for acceleration due to gravity is meters per second squared, that you have to square 9.8. You don't. This is just the unit, meters per second squared. It has nothing to do with the number. So this is not squared here. We don't square 9.8. The unit is meters per second squared. But that doesn't change our calculation. So it's just 60 times 9.8 times 2,000. Okay, different type of question. A boulder rests on top of a 500-meter cliff. It has a gravitational potential energy of 220,500 joules. What is the boulder's mass? So now they gave us the gravitational potential energy, but they want to know what's the object's mass. So I'm just going to write my equation down again. GPE equals mass times gravity times height. I know that gravitational potential energy is equal to 220,500 joules, and that has to equal the mass, which they ask for and we don't know, times the gravity, which is 9.8 meters per second, times a height of 500 meters. So 220,500 is equal to mass times 9.8 times 500 equals 4,900. I'm going to divide both sides by 4,900 to isolate the mass variable. And mass is equal to 220,500 divided by 4,900, which equals 45. And this answer is going to be in kilograms. Okay? Because this equation, again, the units are kilograms for mass, meters per second squared for the acceleration due to gravity, and meters per height. Okay. An 85 kilogram ski jumper has a gravitational potential energy of 9,996 joules. How high above the ground is he? So now they give us the potential energy, the mass, but they want to know the height. So mass times gravity times height. 9,996 joules. It's equal to a mass of 85 kilograms times an acceleration due to gravity of 9.8 meters per second squared times the height. 9,996 joules is equal to 85 times 9.8 equals 833 times the height divided by 833. These cancel. 9,996 divided by 833 equals 12. 12 meters is equal to the height. Okay, how does the gravitational potential energy of a 30 kilogram object compare to the gravitational potential energy of a 10 kilogram object at the same height? Alright, so in this question they don't tell me the height of the object, and so there's no way I can calculate the actual amount of gravitational potential energy these have. They just tell us that it's at the same height. And they ask, how do they compare? Well, we know that because gravitational potential energy equals mass times gravity times height, none of these have an exponent on it. It's not mass squared or gravity squared or height squared. Therefore, if mass doubles, then gravitational potential energy doubles. And if the height doubles, then gravitational potential energy doubles. So if we look at this, 30 kilograms divided by 10 kilograms tells us that the 30 kilogram object has 3 times as much mass, which means that it also has, if it's at the same height, it's going to have 3 times as much gravitational potential energy. Okay? Alright, how does the gravitational potential energy of a bowling ball 5 meters off the ground compare to the gravitational potential energy of the same bowling ball 2 meters off the ground? So, this question is going to be much like the last one. They can't calculate any actual values, but we can compare them. So, if the one bowling ball is 5 meters off the ground and the same bowling ball 2 meters off the ground, then that bowling ball is 2.5 times higher than the bowling ball at 2 meters. Therefore, the bowling ball at 5 meters would have 2.5 times as much gravitational potential energy as well. Or another way you could say that is that the bowling ball at 2 meters would have 2.5 times less gravitational potential energy than the bowling ball at 5 meters. Alright, that's it for our gravitational potential energy video. Tune in for our next video, which is going to be on conservation of energy.